So thanks to everyone for joining. This is Ben Hoffman. Steve and I are going to be presenting the third webinar in a series of New Eagle webinars on a monthly basis. This is on model-based development. So the Raptor toolset allows for, in addition to the embedded development for control modules, we also are allowing development of display models. So you can do your model-based development for displays in the same environment that you do your embedded controls development. This allows for simplified communication between an embedded controller and the display. They can both use the same DVC and the same block interface, which really simplifies communication between the two, and also allows you to re-leverage the training with regards to embedded development. That training for Raptor can carry over to the displays as well. So I'll be online for comments or questions during the webinar here, and with that I'll turn it over to Steve.
All right, thank you, Ben. So yeah, we're going to go ahead and get started with the model-based display development information now. We're going to give you an overview of displays, New Eagle displays, what we're doing with them, Raptor, Motorhawk, how we're all integrating them, and then we're going to give you a demo, and then we're going to cover some special block sets in Raptor for J1939 and Modbus. If you have any questions, just go ahead and ask them. There's a questions bar on the right side of your screen, or whatever GoToMeeting has set up for you. So just ask them there, and Ben will answer them, or we'll take time at the end of a section to answer them. Okay, so our display offerings, we have the CanTrack 1700, the CanTrack line, the 1700 and the 7200s. For these we have non-Raptor libraries like Motorhawk, and that creates a CAN slave basically, so you can control them over CAN. Whereas the VCAN lines, these are color displays, and they range in customization from Raptor, so you can do a full Raptor loadout with, you know, super customization, CAN, everything, and then we also have a CAN slave library as well for the VCAN 320. So we're going to take a quick look at the MiniView 1700 Motorhawk slave here. It takes CAN messages to control it. 64 by 128 monochrome display, Motorhawk library. So there's a video here of okay, so that was developed within Motorhawk, sending these CAN messages to the display to configure it and show what you want on the screen. So that would be using a Motorhawk ECU. But now we're going to move on to the VCAN 800 here. We're going to talk about it real quick. This is an up-and-coming Raptor option. It's a 7-inch 800 by 400 pixel touchscreen. It has a bunch of analogs, inputs and outputs, 2 CAN, RS-232, and it's Raptor enabled. So that will be coming out in the next, I don't know, next release here. But this VCAN 320 here, 320 Lite, this will be the bread and butter Raptor right now. So again, it's Raptor enabled. On 320 Lite, you don't get the analog inputs or outputs. It's strictly CAN and 232. as well as USB. So you can do USB logging on it within our Raptor framework. So here is a breakout of the 320 of our available options for it. We have the C-based data logger. You can put that onto your network and it's ready to start logging all your CAN messages, 2-channel CAN logging, as well as analogs. There's a 320 and a 320 Lite version. GEM software that's comes preloaded on most vCANs, supports J1939, and then we have the SDK option. So if you want to go a full C-coded option and do your own stuff, that's the SDK. But really, we're talking about Raptor today and how to get that going. So real quick, this is the vCAN 320 Motohawk slave library. You drop that into a Motohawk and you can have some quick gauges. Analog gauges, some digital gauges. It's all CAN controlled. So why Raptor? Ben might be able to touch on this, but I'll go through some quick points here. Rapid prototyping, software versus application engineers. We can get the application engineers up and running and get their controls out versus having a software guy write C code all day long. It's built upon MATLAB and Simulink, and it allows the same software with some minor changes to be put onto other displays. Ben, do you want to add anything here?
Yeah, so we, with a model-based approach, it basically takes your model and code generates down to a binary that can be loaded right onto the display. So there's not need for any hand coding. And as I mentioned earlier, the effort to get trained up on the tool set can apply to both the display and the embedded controller. And actually in some cases, like with the vCAN 320 and the vCAN 800 that have some I/O, for simple applications, the display can actually take the place of both the display and an embedded controller using the CAN and the analog inputs and digital inputs and then the outputs to do actual control functions. And you can put in your model, you can put control logic in Simulink and Stateflow, and that'll can take the place of actually an embedded controller in some systems.
Okay. So I'm going to give you some quick demos here. I have a few simulator apps we can check out. So these were all built within the Raptor framework.
So I should mention real quick, when you do a Raptor build in Simulink, you have option to build a PC simulator in addition to the embedded executable, and so that's what we're showing here. Building the PC simulator and having it start immediately after the build is useful to do iteration on your display design, so you can see how things will be laid out. And if you have a capacitor plugged into your PC, the simulator will actually receive CAN messaging from the bus, like if you're connected to your system, and show that live data inside the PC. So this avoids the need to load the executable onto the hardware, which takes a minute or so, and it can cut down on the iteration time.
Yep, thank you. And so the last simulators you saw there were the 320 simulators. This is just a quick demo of the 800 here. It's a larger screen. It's all touch-based, so anywhere on the screen can become a button. So let's go take a look at building one of those. So to create a blank template project, you do a Raptor command called Raptor create display project. And when you first start up, you'll be given this top level here. The ECU definition, you can select your display. The first one is the VCAN Lite, so that has no I/O really. The second one here is the VCAN 320 normal, so you get the I/O with that one. And the last one is the 800. We're going to build for the normal VCAN 320. Oh, and I should also mention that when you build here, you have the option to build for the target as well as simulator. We are going to do a simulator build right now, so that way you guys can see it happen. So I'm going to do a Control B to build. And this is all within the MATLAB Simulink framework. Okay, so some magic happened, and now we have a PC simulator running here. So let's take a look at a blank project and create something. So what I would like to build is a simple application with one gauge that takes in some input over CAN and displays it. So I have a blank project going over here, my VCAN blank. So when you go into the foreground here, you have an option for a splash screen. So this is the first screen you see when you power up the VCAN. There are two splash screens, but the first one here you won't see unless you're on the hardware. So let's look under. So our screen logic is here. We have a screen definition for a splash screen, and off that you have options to initialize it with some things. You can set up the background, and you can also have an update function. So let's add a custom background. Okay, so I just added a custom screen there. And let's do a quick build. Alright, so what you saw here was a custom screen added. And it's pretty simple, but let's add some CAN messaging to it. So to do that, we're going to go down to our plant here, and we're going to grab a can block from our Raptor library. And our can receive block allows you to select a DBC file from which you can select the signals that you want. So I already had one pre-made here. It's going to take in a voltage signal over CAN, and then we can add that into our model here. Now downstream in the display, we want to display it on a quad screen. So we're going to add a quad screen from our Raptor display library. Or rather, in this case, we can use a single gauge. So I'm hooking up the signals here. And we want to grab our CAN signal voltage. And pass that into our gauge. And we'll give it a maximum value of 20 volts and a minimum of 0. The background image you can select. One second, and I am going to go back to a quad gauge just to show you that you can enable and disable these quad screens as you like. So if you don't want one of these quad gauges, so a quad gauge is the 4 gauges on one screen, top left, top right, bottom left, bottom right. So we're going to do one of those, and we're only going to show 2 of them. And in the top left, we're going to have a 0 to 20 and a background image of the one we selected previously. So this will create a quad gauge, but we need to add a button handler to link it over to our splash screen. So from the outputs of our screen definition of our splash screen, when button 1 is pressed, we want to go to quad screen. And similarly, we can go back to the splash screen from our quad screen gauge. Okay, so let's go ahead and try building this and see what happens. We'll add some blank blocks here just for completeness. And let's build. Okay, so button presses switch screens. Screen 2 here. It should be taking a value over can, so we can simulate a can message.
Steve, how do you know which can message to send?
Right. So to know what can message to send, we can go take a look at our sensors here, our can. So this is our can receive message here. You can see can ID 1 is the message we are receiving, and it's receiving a signal at start bit 56 and length 8. And we can take a look at that in a DB viewer to get a better idea of what that means. So this is the signal volts 1, so it'll be at this first byte in the can message on can ID 1. And I think we have the wrong baud rate here. Let me just verify my CAN network real quick. And we have to plug that in. Okay. Okay, so now we're getting CAN messages, so we should be able to send them as well. And we see it jump to a value of 11.1, which matches our expected value here when there's a factor of 0.1. So our gauge updates, but maybe we want to add a digital value to read it a little easier, so we can do that. Here on the quad screen in this update function. Closing out an old project I had open right now. I'm going to open up another project just to show you something real quick. Okay, so this is an element block which does, it handles automatic detection of drawing and dirty areas to the screen and clearing it automatically. And we're going to put that into our foreground of the screen. And we're using a DrawText block, which you can find from our drawing functions in the library. DrawText. So you can specify the text is coming from a port. You can specify the color. We can make it green. Opacity, font, height, alignment, all these things you can set. And again, we're passing in the voltage here. So we're grabbing that same voltage message and we're passing it into a string printf block, which will allow us to format the string as we want. And with the DrawText block, you add in the desired x and y coordinates. So this is from the top left corner, it's 0 based. So 0 to 320 for x and 0 to 240 for y. So let's go ahead and build that. Okay, and now you see we have a text value there of our voltage. So if we send the CAN message, we should be able to see a value of 11.1, and it'll change with the CAN message. Okay, so that's a simple example of adding in a CAN message, displaying it on a screen with a gauge, and screen transitions from a splash screen to a gauge screen. Any comments, Ben?
Yeah, so we've got that other gauge in the bottom right there. If we wanted to add a signal to that CAN DBC and then pipe that through the model over to that gauge, could we do that?
Sure, yeah, I'll demonstrate that. So in our DBC editor, we can add another signal here. We can call it RPM. Start bit 8, length 16. Alright, so we edited the DBC file to add a signal that we're going to drop in there. So we go over to our CAN receive block, and we see that RPM now shows up there. We hit OK, and now we need to add that that signal to our bus. We use our bus selector to select the RPM signal, and we want to put it in the lower right corner. So that will give the analog value. And we'll go from 0 to 8,000 on that. Background image, we can add an image. Do we have anything that looks like an RPM gauge? Probably. Here, we'll just use this one. Okay, so that will pipe in the RPM to the analog gauge. And let's add another digital readout to that. So let's do another one of these element blocks. We'll tap the same sensors bus, but we're going to position it right about here. So if you look in the bottom right corner here, it will show you the XY coordinates of your cursor at the time of there. So we're at 140. Let's drop it right here. So that will be 115 at 200y. So 115x at 200y. And we don't want volts, we want the new RPM signal. And we don't care about the decimal here. We're going to have 4 digits for the RPM. And let's right align this one, so it'll be on the right side. The text will go to the right of where our XY coordinates are. So then actually let's put it at 160y, or 160x. And let's give it a different color for fun. So this should all add a second digital readout for the RPM right here, and it should also update the analog gauge from 0 to 8,000 RPM. So let's try building that. So we have our RPM gauge. Let's send a CAN signal, and we get 100 RPM. Now this is a 16-bit signal, so it crosses 2 bytes. So if we send a 1 in the second byte, we should get a value of 256. Right. And that is off the scale. So it's updating our gauge correctly with a new CAN signal, as well as the background image we selected.
So now that you have the simulator doing the the display the way you'd like, what would be involved in getting it loaded onto the actual hardware?
Sure. So to get it loaded on the actual hardware, we have to build for our target. So we've previously only been building for the simulator, but within your ECU definition block, you select both the device with the code sorcery compiler, and then if you still want to build the Visual Studio simulator, you can, but that's not required. So you can build this now. Okay, so the build is done, and when it's done building, it drops your files into C ECU and then your project name. So my vcan blank. I believe yeah. So it drops the builds into here. ECU my vcan blank, which is the name of your project. Subdirectory 19, which is your build number. And then it gives you a zip file and a README on how to install it. So the README will tell you unzip this and then drop all the files within there onto a USB stick. And then you take all these files, put them on a USB stick, and then plug it into the back of the vcan, and then the update procedure will begin, and you'll have your new application. So, is there anything else I should touch on, Ben?
No, I think that's a good overview.
Okay. We can jump back to the presentation here. I think most of the stuff we already covered here, building and simulating the template model. That was the first thing we did. We ran the Raptor create display command. CAN logging. So we do have the vcan Raptor does support CAN logging. And that is all. So we give you the template project comes with a default CAN1, CAN2 logging. It logs all the CAN messages for you. If you wanted to do specific CAN logging, you could go into the CAN handlers and control how you want to handle the messages.
And how do you create a template project?
The template project, that was the first command here. So Raptor create display project, my new project. So this will give you the base project. It has the CAN logging. It has the couple screens here for you. And that's ready to go.
And where does the logging with the template model? It's got some data logging in it. It shows how to use the File IO blocks, but where does it write that data to?
Sure, yeah. So it will write to the USB stick with a file name here. So disk SDA1, this is the prefix to write to the USB stick. The stuff after it is your desired CAN logging name, so file name. So we see it's myvcan underscore version. So the version is the Raptor build number. And then we're also adding in a another integer to the CAN log here. You can also add the header to the file, so that's the first thing that gets written, and then subsequent writes will be written to appended to the file.
And so this is an example that can be used as a starting point if you wanted to do some custom logging. This example basically just writes the raw CAN from the CAN bus to a file on the USB stick, but it's a starting point if you wanted to write some other data. Might be useful if you had to do service troubleshooting, to capture data from the system at a higher rate than you could with MotoTune or another tool.
Right. Yep. You can also log the analogs in addition to the CAN. Any information you want to log to the USB is well within your bounds. So we also have a J1939 library that's integrated into Raptor. If you're familiar with J1939, you'll know that there's PGNs and SPNs, and we make that really easy to handle and to send out onto the network. And again, that's all integrated into the Simulink library here. So you go to your Raptor J1939 toolbox. You drop in a transport protocol block, and now you have J1939 support. As soon as you add some other PGNs here to send out. So you don't have to mess around with all the J1939 specifics. You can just get going here. We also have a Raptor Modbus library, and that allows you to do Modbus master requests. So you can request RS-45 data from a Modbus slave and get that into your application pretty easily as well. Okay. Any other specifics, Ben, you can think of?
You might show the File IO blocks that are used with the logging, so where those are located in the Simulink library.
Sure. So a Raptor data logging library allows you to add the Raptor File IO. So you have your data logger read blocks, your write blocks. You have your erase, your USB status. So is the USB ready to eject? Is it inserted? And those will help you to know if the USB is plugged into it, and you can start logging. And these are made use of in the example logging we give you. So you see there's a file write block here, which we take from that Simulink library. And we pass in a formatted string with a bunch of information, the CAN ID, length, our 8 bytes of data, and the time. And that all gets combined into a single string and written onto the USB with a file write command. So what else can I say about this? USB and status. So if it's inserted, then we go ahead and So the first time it's inserted, that's what the trigger there means. So when it's first inserted, we create the file and we write the header. Again, if you're using our template, the only thing you really have to know is to change the file name that you want, and then the header. And then while it's running, these can triggers will do the file writes, and then periodically we do a file sync to make sure that the USB is up to date with our data buffers. So, anything else to add here, Ben?
There's a question about the key handling, how to switch screens. So in response to somebody pressing a key on the one of the buttons on the front of the display, how does the model accommodate that to cause this switching screens?
So the question is, how do we switch screens? How does he? So basically when we're doing screen switching here, we start with a single screen, a splash screen here. This is our initial screen as shown with the set initial here. So this forces a screen to go to a certain, or forces the vCAN to go to a specific screen at start, and we chose the splash screen. So to switch, we have a digital input. We consider all of the 5 buttons on the vCAN to be a button hardware resource of a digital input. So button 1, 2, 3, 4, 5, and then we trigger on that on the falling edge, and then we go to the quad screen with a go-to screen block. And this go-to screen block is one of the it's available within the Raptor display library from the screen functions. So display go-to screen, and when that is triggered, it will go to your set screen.
So then when you're at the other screen, you would need to have some handling to switch to a different screen.
So to switch to a different screen, so the go-to screen block will switch to your desired screen. If you wanted different button handling to go to other screens, then you would configure these buttons as you like to go to other screens.
Okay. So I think we have some time. If there's any questions on either Raptor or the vCAN display development with Raptor. Okay, I've got a question came in wanting to show again how to add another screen and how to have the switching of screens handle 3. Looks like we've got this example toggles back and forth. Maybe we could add a third screen and then configure the button handlers to using the two. Right now we've only got one button configured to have the two buttons to go in a cycle.
Okay, so I see a bunch of questions here. Let's start somewhere. 1 second. Let's see, do you have your old webinars recorded and shared over your website? Yes, we have them. We'll send that out to your email. Does Raptor support J939? Yep, we went over that. What provisions are there for drawing custom graphics on screen if you don't want to use one of the pre-configured gauges? So in our update function, you can see we have a DrawText. We also have other drawing functions like you can draw a polygon, you can draw an image, and then if you draw an image you can just grab whatever image you want and drop that right onto the display. And there's other options like draw a circle, clear rectangle, stuff like that. Is there an object for real-time plotting of CAN data? So again, that would be, we have the analog gauges, but if you wanted a real-time plot, you would have to create, you could create something in Raptor for that.
There's not a pre-built logging or plotting component presently, though.
Right. Do the displays have dimming capability via CAN message, hardwired input, or both? So yes, we can control the backlight on the screen, but that option escapes me how to do that right now. There should be a Raptor block somewhere that allows us to control the backlight and contrast on the screen. Another question, does this support custom animated graphics? So whatever you can build within Raptor with images and analog gauges,
so typically when we've animated an image before, for instance like a battery gauge, we will draw the battery, kind of like empty, and then animate it via draw image and draw the slices, which indicate the state of charge basically. So it looks like it's filling up as it's being charged. So it's kind of animated, but it's not. You do it with the draw image. In fact, in the display library, there's an example of a battery gauge that can be used as an example of how to animate something, and that's included with the in the Simulink library.
Yep. What options do we have for screens and gauges? Are we limited to analog speedometer style gauges that you've shown? Can we use bar graphs or custom gauges we create ourselves? In the quad screen, can we say configure the two right quadrants to have gauges and display an image across the left two quadrants? So yep, screen is fully customizable. Whatever you want to draw onto the screen, you can definitely do. Create your own gauges. The quad screen block is these outputs here are to allow you to customize it however you want. The create background and the update foreground. Can the user combine some Motohawk and Raptor blocks in the same project? No. So Raptor is its own platform. You can only use Raptor blocks. So each screen has to configure what all of the buttons do while on that screen? Correct. So each screen you configure all the buttons. So if you wanted to add button actions for all of them, you would add button 1, button 2, button 3, and you do this for all the screens. Now if you had similar button handlers for all of them, you could turn this into a library block or just copy and paste it. And then you get the same button actions for all the screens. Can you read DM1 messages, multi-package, and display fault codes on screen and log them?
Well, you could use the 1939 transport protocol PGN read, and that would provide you the content of the DM1 message. We don't include a parser for it. The 1939 block set is geared more towards the sending side of things. So the multi-packet nature, that would be handled by the transport protocol, and it would provide you the full content of the DM1 message, including the packaging of it if there were multiple frames. But parsing it, it's not presently an automatic feature.
Okay. Is DBC support included with Raptor? Right now with Motohawk we need the CAN networking toolbox. So yes, DBC is our default fully supported CAN messaging. Can you touch upon the concept of probes and overrides with respect to Raptor? What tool will we be used with Raptor in place of MotoTune? Ben, do you want to take that one?
Sure. If you want to open up the Raptor library, you can go to the data storage area. Now, Raptor supports XCP as a calibration protocol, so there's a number of tools that you can purchase from Vector, ATI Vision, Canopy, Inca. Those are all supporting XCP, and we generate a A2L file that is compatible with those tools. So you can use any standard commercial calibration tool. We also support towards the end of this year, we'll have a New Eagle calibration tool that will be a lower cost alternative to those third-party tools. So you could drag in a override and a measurement. So the measurement is the, and those just hook to any signal, and then that data is exposed in the calibration tool.
Okay. Can we please talk a bit more on J1939 or take a webinar on this topic in the future? So in the past, we have taken a webinar on J1939. That was the Motohawk one, though. So we can add.
So I would say the link to the presentation from last month's webinar series. That is available. The block sets are nearly identical. The supported features and product options for the 1939 block set for Raptor is very similar to what was presented in last month's webinar. So I would say to start there, and then if there's any questions, we will look at the webinar schedule, but there would be a lot of duplication between the you know, it's a protocol block set, so there's going to be a lot of similarities between the two. So we'll look at putting that maybe on the schedule for a Raptor J1939 block set presentation.
Okay. Can the display be used to send values to the ECU? For example, calibration of some values inside the ECU. So yep, that is just a simple CAN transmit message here. In this CAN message, we are sending out the analog 1 value we read from our analog input as well as the power supply, and that gets transmitted onto the bus in this this CAN message. So ID 111, that's in the example template project. Have all the Motohawk blocks been replicated on the Raptor? How easy would it be to migrate? Ben?
Well, so obviously the display blocks are only targeting the display, and we've kind of covered the way that CAN messaging uses DBC files. There's blocks for common ECU features like digital outputs and PWM outputs and analog inputs as well. So those common features are the same.
Okay. Do any of the analog gauges have a damping setting to make the gauge appear more realistic, i.e. not move the needle instantly? So that is something you can add within your model. It shouldn't be too difficult to add an input to delay some values or integrate them or otherwise, something like that. Is Simulink model referencing with bus capability supported with Raptor? No.
Model reference is presently not supported.
Okay. That's all the questions we have here. Any final remarks?
No, we've consumed the time, the hour that we had set aside, and we know that everyone wants to get back to their normal activity. So thank you for joining. If you go to our website and take a look next month's webinar will be around this time in August, and we hope that you can join us. Thank you.
Thanks.